Hello, we would like to welcome you to our presentation, which is entitled From Science to School, Educational Transfer Research of Modern Science Topics in the Interplay of Curriculum Development and Empirical Research. In the background, you can see a teacher training where a specialist in inorganic chemistry is giving a lecture. As teacher education can be separated in the fields of content knowledge, pedagogical knowledge, and pedagogical content knowledge, we would like to present a project that tries to combine those three dimensions regarding teaching as well as research. We, Teresa and Philip, are part of the Chemistry Education Department of the Friedrich Schiller University in Jena in Germany. First of all, we will present the project's structure and its embedding in current challenges in teacher education. Next, we will focus on two examples of the project's outcomes. Finally, we will give some perspectives and outlooks on the further development of the project. Since 2015, numerous project initiatives have been founded throughout Germany, as you can see on the right, within the framework of the qualitätsoffensive Lehrerbildung, in which a contribution is made to the promotion of teacher professionalization through greater coherence in teacher education. In fact, a first attribution of coherent teacher education is to link the three knowledge dimensions, as I mentioned before, content, pedagogical, and pedagogical content knowledge, referring to the classification by Schulman, CK, PK, and PCK. However, collaboration between all players in teacher education within university frames, called intra-phase coherence, is just one part of coherent teacher education. You can divide into vertical and horizontal coherence, as well as into synchronous and consecutive coherence. Horizontal coherence goes hand in hand with intra-phase networking, for example, when courses are jointly designed by subject and subject education. The development of a deep structure within a discipline, for example through the application of theoretical knowledge in practical situations, can be described as vertical coherence. Synchronous coherence is present when, for example, pre-concepts are discussed in the subject education and the constructivist foundations are discussed in the same time in the educational sciences. The construction of a spiral curriculum, keyword cumulative learning, or also the interweaving of the phases of teacher education, which is a cross-phase cooperation, can be interpreted consecutively, i.e. chronologically. Eventually, relevant subject specifics, e.g. the methods for gaining knowledge in the natural sciences, or holistic educational concepts like education for sustainable development, inclusion, democracy, education, and so on, can also be integrated into the discussion on coherent teacher education. At the center of our project is a Learning to Teach lab that includes innovations in subject education, for instance by regarding new contents for school education, and learning processes, for example the interaction of modern teaching materials and students' activity. The project is characterized by the interplay between all players of teacher education. Target groups can be teachers, for instance in teacher trainings, teacher students, like in seminars, or even students in school projects. An important link is the cooperation between subject experts and subject education. Whereas the subject provides the professional input to a certain topic, the subject education is responsible for what we can call educational reconstruction. The aim of such a collaboration is the development of new school experiments, scientific models, or just teaching ideas, you could say incentives for modern teaching. Last year, we focused on the field of self-healing materials in an intra-phase cooperation between subject education and the Institute for Organic Chemistry. Self-healing materials are known from mobile phone films or from self-healing asphalt and concrete. Besides, self-healing is often found in nature, e.g. the axolotl or muscle biceps or wound healing. Not to forget self-healing polymers as a major area of research. As a result of that collaboration project and the reconstruction of this research field for schools, we would like to present two model experiments. The first one deals with self-healing asphalt. Self-healing asphalt is based on a composite of bitumen, little stones, and, that's the special thing, steel wool. By means of inductive heating, fine cracks in the asphalt are thus be healed by melted bitumen. In a model experiment, a mixture of candle wax and graphite flakes is used. In an electromagnetic alternating field, which is the microwave here, the mixture begins to melt so that cracks are healed. As a comparison, it can be shown that pure wax does not melt in the microwave. The second experiment focuses the biceps, that is, the adhesive hair of California mussel, which shows a self-healing mechanism in stress-strain experiments. During stress, for instance when a wave hits the muscle, the hair is stretched beyond its yield. Only after some time, the original mechanical properties are restored. This is due to the structure of the hair, including coordinative bonds between zinc irons and histidine-rich proteins on the one hand, and proteins with better sheet structure on the other hand. When stretched beyond the elastic range, the coordinative bonds break at the yield point. The folded sheet structures are abruptly unfolded by the acting force. When stretched again, the curve is clearly flattened as now only the better sheet structures contribute to the modulus of elasticity. After some time, however, the coordinative bonds are formed again. This process was simulated in a model experiment, which you can see on the right, in which twisted rubber bands represent the better sheet structures with its hidden length, and further rubber bands with magnets represent the proteins with coordinative bonds. The resulting stress-strain diagram corresponds to the diagram of the muscle biceps. In order to bring this or similar subject education development to schools, my colleague Teresa will present a research design for a school project with a focus on an observation study now.
To produce modern topics into teaching materials, concepts like the curricular innovation research, the participative didactic action research, the curricular transfer research, and the didactic reconstruction are incorporated into the development process. To investigate the use of such curricular innovations, an empirical research design was developed based on the topic drugs within the context of chemistry teaching. For the present research work, a total of 10 stations was constructed according to certain criteria and can be assigned to the theoretical, experimental, creative, digital, and playful learning occasions. The focus is on the illicit drugs amphetamine, methamphetamine, and MDMA or ecstasy. In order to transform the modern topic of amphetamines into teaching materials, teachers, students, non-university institutions, and university disciplines were involved in the conception and optimization. Figure 1 shows the own research process, which is based on the model of didactic action research. The first phase on the left shows that the learning modules have already been tested and evaluated several times with students and teachers. The second phase illustrates the pilot study in which 31 students participated in December 2019. In the main study, the data collection was conducted with students at the age of 16 and 17, or grades 10 and 11. Questionnaires in a pre-post design are designed to collect feedback on interests and prior knowledge regarding the topic as well as acceptance of the program and the individual stations. Short-term program effects on content learning gains will be asked in an open response format in a post-test. The way in which the test persons work through the station and which process-related competences can be observed will be documented by a trained team of observers. The focus was set on observing the processing of the stations in collaborative work forms. In order to generate reliable data and objective assessments, adequate observer training was designed. The goal was to explain the development measurement instrument with associated training manual to the observers in step 1. In order to become familiar with the method and to gain a feeling for the sensitivity of relevant behaviors, a video simulation was planned to determine observer agreement with the measurement instrument in step 2. The next 3 steps made it possible to adapt and optimize the measurement instrument and to provide additional practice sessions for the observers. In the main study, a trained team of observers codes the measurement instrument parallel to the intervention. Thereby, the observers take the role of pure observers without interacting with the research field. To ensure a laboratory study with a continuous framework, each observer acts as an expert of an assigned station for the entire phase of the main investigation. The design and content of the measuring instrument was based on work from the fields of chemistry didactics, pedagogy, psychology, and classroom research. 4 main categories are defined for the documentation in Figure 4. The 4 main categories are work behavior, communication, cooperation or social behavior, and dealing with learning materials. Each main category is broken down into 3 observation foci, which are assessed by 4 evaluation scales. In addition, a column with comments and a field for special anomalies are provided. The goal is to investigate the way students work with the new materials and social forms of work.
Okay. We presented a procedure in which current subject content was developed for teaching at the interface of subject and subject education with socio-empirical evaluation. Besides this work, our project includes tandem teacher trainings, like the tandem of subject scientists and subject education experts, early practical experiences for teacher students, as well as courses on inclusion, digitalization, or interdisciplinary teaching. As an implementation strategy for those innovations, digital learning communities will be established. Following the idea of professional learning communities, they translate subject education and pedagogical as well as curricular innovations into everyday school life through cross-phase cooperation between university and school. Thank you for your attention. We are looking forward to engaging with you in the comments below.